I guess it works. Great. All right, so now we're going to talk about sequences. So have you guys actually done sequences? I'm being serious.
Yeah.
You have? I know you have. Probably pre-cal here in grammar, you probably haven't. So basically sequences, we're going to keep, and I think that's kind of important, the domain is a set of all positive integers, okay? So we're only going to be dealing with n. N is going to be a positive integer. So if you think about it, right, a1, for example, let me zoom in on here. A1 would happen when you just plug in a 1 for n over 1 plus 1. So that would be 1 over 2, right? So that's basically how they're getting that. And then they would plug in a 2, and you get a 3 over 3, which is 1. And then you plug in a 3, and you get a 5 over 4. And you plug in a 4, and you get 7 over 5. And then dot, 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 right? It just keeps going, right? So in terms of this one, if you plug in a 1, so a lot of these, especially on the homework, you can kind of do it. I mean, if you absolutely want to use the calculator, use it. You can put this as y1 and look at the table, right? But this is 1. This is B2 would be 3/4. B3 would be 7/9. B4 would be 15 over 16, etc., etc. I mean, it's pretty straightforward. There's no trickery here. Does that make sense? We're just plugging in positive integers. That's the main thing. We're not going negative. We're not using 0. Okay, now there's also something called a recursive defined sequence. All right, recursive means you're going to use the previous number. All right, so for example, on the first one, all right, let's say we're looking, we know that a of 1 is -1. We know that. All right, a of 2 would be 2 times 2 minus 1 here would be a of 1, which would be -1. So we're using the previous number. That's what that does for you. This right here means you're going to use the previous number, which is -1. Okay? And then we're going to have a +3. Well, thank you, Brock. It's very impressed. So we have a 1. Okay? Now, if you think about it, you can kind of look at this, and without actually having to write it down, you can sort of see what's going to happen, right? The next one for a of 3, well, I shouldn't go up there. A of 3, that would be 2 times 1 plus 3, which is 5. So we're always using this right here stands for the previous number. So the next one would be 2 times 5 plus 3, which is 13. And so on and so on. Does that make sense? So the recursive sequence just basically implies you're going to use the previous number. Okay? Make sense?
Yep.
Okay. Same idea on here. I'm just going to write them. Doesn't really matter. This would be 5. B2 would be 5. I found a way to do some of these straight up on the calculator, the recursive ones, but I just let you look that up on your own because sometimes it gets more complicated. All right, now this is the fun part, / not really. All right, this is actually my least favorite part because I have to figure out the sequence. The first sequence is not that bad. So can you figure out a formula for A that would give me those numbers? Now, remember that the first one, A of 1, whatever formula I'm doing here is going to give me 1. The next one is going to give me -4, and then -7, negative. You notice a sequence there, right? What's happening?
Subtracting 4.
You're subtracting 4, okay, every time. But I got to do it in a way that the first time I do it, I get 1. So what should I, if I'm subtracting 4 the entire time, what do you think that would be?
5.
5 minus 4, right? So we can write this as, this just implies that we have a sequence, and then we have 5 minus 4n, where n is a positive integer. Remember that, right? It has to be a positive integer. This one's more fun. I was feeling pretty good about myself on A, and then I got to B, and I didn't know what was happening. All right, so, but actually, it's not that bad. I just wasn't thinking. I'm not that. Sometimes I should think more like this, but I don't. What pattern do you see?
The denominator is increasing.
The denominator is increasing, right? And as a matter of fact, we can even say that this one, it's 1, right? If we put -1 over 1, we have 1, 2, 3, 4, right? So could we say that this right here would be n, right? A1 is -1. Now, I got a -1 the first time, so I know I need to have a -1 at the beginning, right? But on the second integer, I have a positive. and then a negative, and then a positive. So how would I write that? What do you think?
How does the negative work?
Well, for the first one, that would work, but I need to find a way that all I need to do is plug an n into it. So I'm going to write it. Unless somebody's going to tell me right now.
Times.
As to the power. Power of n. Very good. All right, so the power of n, think about it, right? If we raise this to the second power, right, that's going to make that a positive 1, right? And that would be 1 over 2. So anyway, moving on. Now that I built you up, let's see. I don't know. Yeah. What do you think? What pattern do you see? Well,
N over 2.
you're square root of n over. Oh, excellent. You just told me right away.
Give it a shout out.
Now that took me a little bit to find out, but then I had to figure out that this right here was originally.
That's Brody right there.
Yeah, that was Brody, by the way. Credit forever on this video. What was it that I put? Oh, that's right. This originally must have been a 4 over 16, and that's sort of how I figured that out. Because if you take the square root, that would give you 2 over 16, and then if you reduce it, you get 1 over 8. Okay. All right. By the way, that was Brody Heseltine, perhaps the brightest mind, and in my 5-person class in BC. All right.
Ouch.
You just said perhaps.
Perhaps I didn't say it was. All right. What do you think about this one?
Simply not the woman.
Oh, easy. This is a. Hold on. This is a video that will go on the internet. I cannot have sexism on this. Okay.
But it's like
Stop. All right. So, what do you think?
Well, it goes from 1 to 0.
Right. So think of.
Hold
on. Think of a generic function that would go from 1 to 0 depending where you're at. You've done it before.
Function.
It is a trig function. Go ahead.
Sine.
Okay. I guess this one could probably have. I can see this one having a different function than this. Should have written brackets here. So again, sometimes you might have something different. I think cosine would work also. If we would have written like cosine of pi.
Why is it
Negative.
pi over 2?
Well, just think about it, right? If I plug in a 1 here, sine of pi over 2 is 1. If I plug in a 2 here, that would give me sine of pi, which is 0, and so on and so forth. Okay, move on. Moving on. How long do I have here? 1:49. Okay. Got 10 minutes. All right. So on this one, I'm going to move relatively quickly through these. All right. It turns out that you can take limits. Now for this one right here, all right, we're going to take the limit as n goes to infinity. Okay, in all of these. And then sometimes it's pretty easy to tell what's going to happen. Meaning you can kind of see, okay, like something may go to 0 or something like that. But in this one, I actually had to plug it in the calculator. So you could do that also, okay? You can plug it in the calculator, and you can always do something like this. Well, I'll just show you here. All right, if, let's see, we can have something like this. And then you're going to probably tell me, hopefully pretty quickly, what you think this is. And basically, when we raise something to infinity, we want to find out if it's going to be diverging, meaning that it's going to one single point, or if it's converging, meaning it's just going away from any point. It's not focusing on one single y value, if you will, right?
It converges. So what?
No. Here. So I'm just showing you in case when you have this, either the test or the homework, okay? This is how you could figure that out. I'm just going to go to the window. Excuse me. I'm going to go to the table, and I'm going to start this at 100 because I just want to see what happens, right? So if I go to the table, notice that these numbers are basically not getting any much bigger than 2.7 something something. See what I'm saying? Is there a constant that you remember?
E.
Yes. So this right here is E. Okay. Now this one's actually not that bad. I guess you can use the calculator too, but this one you could definitely do it without. So what is the cosine of 1 over a really, really large number? Right, how'd you know that? Right, because this is approaching 0, right? So we can say that's the same thing as that. Yes, excellent. And some of these are, you could plug this in the calculator or not. This one's easy enough, you don't have to, right? What's the only thing that's going to change on here? It's going to go from -1 to +1, from -1 to +1. Does that make sense? So for example, if I write B1, that's 4. B2, which means I would square this, that would give me a +1, so that's going to be 6. If I plug in a 3 here, that's going to give me a 4 again, and then a 6, and then a 4, and then a 6, and a 4, and then a 6. Brock, you look confused. Why?
There's so many letters and numbers.
All you need to focus in. I know that this looks confusing. Do not focus on this. I'm just telling you that's the name of the function.
Okay.
Okay? Just focus on this. And n is a whole number, and it has to be positive.
Okay.
That's all I'm saying. So if this is to the first power, that's not going to change this, right?
Yeah.
That's just going to be 4. If this is to the second power, that's going to make that a +1. 1 plus 5 is 6. All right. So anyways, is this converging or diverging? Diverging. It never goes to one single point, right? Yeah. So we can say the limit as n goes to infinity of b of n like that, so we don't have to write the whole thing, the whole function, we say is diverging. Are you with me?
Yes.
All right. This one a little bit more difficult. Okay. But I'm going to show you a trick here in just a second. Just go with me. I had to plug it in my calculator, and I got 2/3. Okay, so the limit as n goes to infinity of function b of n like that was -2/3. Yes. Okay. Are you with me? Now, I know you don't get why I got that. All right, you can plug it in your calculator, but it wasn't until I got to here that I realized that I could do it a lot easier had I known this ahead of time. You can use L'Hopital's rule. Now, do you remember when you're allowed to use L'Hopital's rule?
And the limit goes to infinity or
Infinity over infinity, plus or minus infinity over infinity, or 0 over 0, right? So we can have that. Now, the question for you is, does this, oh man, does that go to infinity? That looks like an H, but this is definitely not. Yeah, that definitely gives me this, right? So I can use L'Hopital's rule. And yes, I did not misspell it. Okay, and did not call it. Did not call it Le Hospitals or Hospitals rules. All right, so we're gonna use that. So what's the derivative of n?
4.
Now this is the one you may not remember because we don't do it very often. Do you remember how to take the derivative of an exponential function that's not e to the n? You probably don't. Okay, go ahead. It's 2 to the n. It's 2 to the n. Listen, it's 2 to the n times the derivative of 2. Excuse me, the derivative of n. What's the derivative of n? 1 times the natural log of 2, and that's what I honestly I had to look it up. I couldn't remember. But that was from calculus AB. We just did it so very briefly that we missed it. Okay, so anyways, what happens here if I plug in a really, really large number at the end?
It's infinity.
Infinity. So what do I have? 1 over a really big number. 0. Correct. Okay. Now, you see how what I'm saying about this one? I could have used L'Hopital's on B and got that answer right away. The derivative of 2 is 2. The derivative of the bottom is -3. I could have got that. Okay. I'm going to pretend like you know how to do this one because I'm running this down. Yeah, so if you get a single number, like this is be converging. Thank you for reminding me. Now this one right here, again, you can use, on this one, you actually use L'Hopital's rules twice, all right? Because you do it once, and you still get infinity of infinity, and you can do it again. And once you do it again, you'll get 3/2. So the limit, so I'll let you do this one on your own if you want to do it. Thank you. I may have to stop early, but so this is converging. Okay. All right. Moving on. Now we have all these definitions that sound kind of difficult, and I think this is the end. All right, so I'm going to kind of speed through in this. Now we have the definition of what I can only assume is pronounced monotonic sequence. Okay. Now this I found that really weird the way they wrote that. They wrote that as a non-decreasing function. But if you look at the definition, it could be increasing. That's really what it means. It's increasing, right? Because notice that the number that comes after is always bigger.
Yeah.
But also it can be equal, which means it can be completely flat. Does that make sense?
Yeah.
And this one right here, the non-increasing is really decreasing, but also can be flat. So that's what I call a monotonic sequence, all right? Now the definition of bounded, and you can read the definitions. I assume you can read in English, but maybe you can't. I barely can. But the point here is that you can't really, I'll show you what that means. Basically, you have to have a bound below and a bound above. And if you do, then this is called a bounded sequence. So let me go to example 1. This is a decreasing sequence, right? Or we can also call it a non-increasing sequence, which I really hate that name, but I can see why they say that. They can't quite say, at least in the definition, decreasing, because sometimes it may be equal, which that means you would have a horizontal line. All right. Now decreasing from left to right. Is it bounded? Well, it is bounded, right? Because here the first number, it's always going to be bounded somewhere, top or bottom. It just may not be bounded both, right? So this is bounded up here. Okay. Now is it bounded down here? Does this look like it's approaching the same value?
Yes.
It does. So it's bounded on top and it's bounded on bottom. So this is why I can say that this is bounded. All right. So again, if it's bounded above and bounded below, then that means that it's bounded. Okay. That's the definition of bounded sequence. It's a monotonic. Yes. If it's decreasing, then yes. If it's decreasing, increasing, or basically a constant, then it is. Okay.
So it always is.
No, not this one.
Oh.
See what I'm saying? And we can say that this is going to converge. Go away. I'm recording. Get out of here. You ruined it. All right. He actually didn't say anything. My bad. All right. So let me quickly go through this. All right. We're almost done. All right. Increasing, you can agree?
Yes. I think it's non-decreasing.
Yes, it is a non-decreasing for sure. Is it bounded?
Yes.
Yes.
But
Yes.
Bottom, and it's pushing some of it.
Right. And that kind of took me a little bit because I was like, well, what about this, right? You know, what happens if I go left? Well, I can't because it has to be a positive number. N has to be a positive number, which means I always start at 1. Does that make sense? Or with N is equal to 1, I should say. All right, so it's bounded. If it's increasing or decreasing, it's definitely going to be monotonic. Monotonic.
I think one is monotony.
It might be. I mean, for all I read it, I don't know. I mean, I've only been speaking English for about 20 years, but what does it converge to? Correct, right? So right here, it kind of converges around right there, which is 6. The Broad Dog still in the limelight here. All right. Monotonic. There you go. That sounds pretty good. All right. We can agree this is oscillating, right?
Yes.
Is this bounded?
No.
It is, right? It doesn't go below here, and it doesn't go above that. So it is bounded.
Just keep going, keep going.
Yeah, we'll keep going. Bounded. Is it monotonic?
No.
No. Because it's not increasing.
Well, not consistently.
Right. If it's basically if it's oscillating, it's not going to be. Either has to be increasing or decreasing or constant. Okay. And it's divergent, all right? Divergent means it's not gonna go to one single point. What? Oh. Ooh. Sounds so crazy. All right. D. Increasing.
Increase.
Or what was the other name? Non-decreasing. All right. Well, we got to really think about it.
It
Like,
is.
You think it's bounded?
No, it's not at the top because you can still.
Not at the top, correct. It's bounded here,
That's what I
but
meant.
it's not up here.
That's what I meant.
So it's only bounded below, but not bounded above, right? So this is going to be not bounded. Is it monotonic?
It is
Yes.
bounded. Yes.
Monotonic. All right. Is it gonna diverge or converge?
No.
Diverge. All right.
No.
Yeah, but it's like, no, that's not really a choice. But you understand why that's diverging, right? It's not approaching a single y value, if you will, right? It's going up. It's going towards positive infinity.
Flip it around.
Here we go. Here.
Does
Does that work for you?
That's some quality stuff there.
I know it's a quality camera I have here.
Jumping over here.
Come on in, guys. Look, I'm done.
Right. Well, if I do it like this, is that upside down?
Yeah, well, that's normal.
You gonna edit this out anyway?
No.
Wait, you're just focused for like a
Bold
minute.
of you to assume we get
There it is.
that. Why do you have your pictures where?
Alright, Jordan, give him the vlog intro.
Oh. What's up, vloggers? We're back at it. Back at the Home Green vlog. Follow me on broccoli_32
Oh my God.
or bhomegreen01 on Snap. Hit up my line.
This is embarrassing. Goodbye.
Bye.